One of the most useful and interesting results in complex numbers is Euler's identity, which says that we can think of cosine theta plus j times sine theta as e raised to j theta. Okay, we'll start with I'll start with the proof for this, and then we will derive a few related identities, and I will talk a little bit about why this is useful. Okay. Now, the main idea in proving this result is by considering series expansions for the functions that are involved here, namely the cosine function, the sine function, and the exponential function. Okay, a Taylor series expansion for these trigonometric functions, or really a Maclaurin series expansion around 0, is given by these two expressions here. Okay, so cosine theta can be written as 1 minus theta squared over 2 factorial plus theta to the power 4 divided by 4 factorial minus theta to the 6 over 6 factorial plus so on and so forth. And sine theta is given by theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial, so on and so forth. And e raised to theta has a series expansion which is given by 1 plus theta over 1 factorial plus theta squared over 2 factorial, so on and so forth. Now, given these series expansions, it's relatively straightforward to verify Euler's identity. So for example, if we take this expression and then we take the expression for sine theta, multiply that by j, and then add them up together, notice what we are going to get is the following. So let's look at cosine theta plus j times sine theta. Okay, so what we are going to end up with is 1 plus j theta minus theta squared over 2 factorial minus j times theta cubed over 3 factorial plus theta to the 4 over 4 factorial plus theta to the 5 over 5 factorial minus so on and so forth. And notice what we get if we take the series expansion for e raised to theta and replace theta by j theta. Replace theta by j theta in the series expansion for e to the theta. So that gives us 1 plus j theta plus j times theta squared over 2 factorial plus j times theta cubed over 3 factorial plus j times theta to the 4 over 4 factorial, so on and so forth. Just write one more term here. But since j is so now if you look at let's compare these two expressions, and we want to see that they are essentially the same. Okay, so we can see that by noticing that each of the terms match up. So we have, so let's see, we can see that these two terms are the same. Clearly these two are the same. Now since j squared is equal to -1, then we can see that these two are the same. And now since j cubed is the same as -j, these two are the same. Now j to the power 4 is 1, so these two are the same, and j to the power 5 is 1, so these two are the same. And you can essentially see what's going on here. Whenever we have something of the form j theta raised to 2 times k, now this is equal to j squared to the k times theta to the k, which is -1 to the k times theta to the k, which is equal to either negative theta to the k if k is odd, or is equal to theta to the k if k is even. Okay, and in the same way, if you have j times theta to the 2k plus 1, it's going to be either negative j. So if you have j times theta to the 2k plus 1, you're just going to have an extra j everywhere. So you get negative j times theta to the, oops, this must be 2k. If k is odd, and this is j times theta to the 2k plus 1 if k is even. Okay, so we're going to see that you're going to get alternating positives and negatives, which matches up exactly with the expression for cosine theta plus j sine theta. So this proves Euler's identity, which says that e raised to j theta is cosine theta plus j times sine theta. Okay. And in fact, one thing that may confuse you is to try to interpret what e raised to j theta means. I mean, the way I think you should think about Euler's identity is as follows: is that e raised to j theta does not have a natural meaning as unlike in the case when you have e raised to theta, where theta is real. Right? If you have e raised to 5, for example, there is a natural meaning for raising e to power 5 or multiplying e with itself 5 times. But if I have e raised to j5, it's not, I mean, that does not have a natural meaning. What is the meaning of e raised to j5? Well, Euler's identity essentially says e raised to j5 simply represents the complex number cosine 5 plus j times sine 5. Okay, so it just means it gives him some meaning for what e raised to j times theta is. But the interesting thing is, we want to think of cosine theta plus j times sine theta as e raised to j theta, because sometimes algebra with e times j theta is easy. So for example, if I have two complex numbers, so I mean, what I'm trying to do here is to try to tell you why we care about Euler's identity, right? So why do we care? Well, we care for many reasons. One of them is the following: it makes algebra easier sometimes. So for example, if I have a complex number, say this is cosine theta 1 plus j sine theta 1, and I have another complex number z2, which is cosine theta 2 plus j sine theta 2. And let's say I want to multiply them together. So z1 times z2. Well, I can either multiply them by thinking of them as just complex numbers in Cartesian form, and then I will end up with something like this. I would end up with cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus j times cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. Okay. Now, and then you could perhaps use trig identities for cosine theta 1 times cosine theta 2 minus sine theta 1 sine theta 2, so on and so forth, and then simplify this further. Okay. Or if you use Euler's identity, which says that z1 is actually e raised to j theta 1 and z2 excuse me is e raised to j theta 2. Now z1 times z2 is e raised to j theta 1 times e raised to j theta 2. The point is, we can manipulate e raised to j theta 1 and e raised to j theta 2 using the rules of multiplication that exponentials follow. For example, e raised to j theta 1 times e raised to j theta 2 is e raised to j times theta 1 plus theta 2. Okay, so now you can use Euler's formula and then convert it back if you want the answer to be finally in terms of Cartesian in the Cartesian form. So now if you apply Euler's formula again, this gives you a very nice and simple expression which tells you z1 times z2 is cosine theta 1 plus theta 2 plus j times sine theta 1 plus theta 2. Now notice that it's really much easier to take this route to finally arrive at the answer. You could do this here, but it's just a little more complicated. Okay. So I think that, and so this is that's why Euler's formula is fairly powerful and it's used a lot. Now, a few consequences of Euler's formula are very important. So first of all, Euler's formula says e raised to j theta is cosine theta plus j sine theta. And if you replace theta by negative theta, what you will get is cosine of, so e raised to negative j theta is cosine of negative theta, which is the same as cosine theta, plus j times sine of negative theta, which is negative sine theta. So you get negative j times sine theta. Now, as a consequence of this, if I add these two equations together, notice that what I get is, if I add the two equations together, the two sine theta terms here and here will cancel out. And so I will be left with just cosine theta on one side. And so I will get the expression that half e raised to j theta plus e raised to negative j theta is equal to cosine theta. And 1 over 2j times e raised to j theta minus e raised to minus j theta is sine theta. So these four expressions together are very useful in doing manipulation. And you should really memorize them and become very familiar with them. And notice that sine theta is 1 over 2j times e raised to j theta minus e raised to minus j theta. Let me make this very clear here. Okay, I've seen a lot of students forget this j.